So good evening. Today we'll be discussing assignment number 11 and I'll be sharing my screen. I hope you can see my screen.
Yes.
Okay. Yeah. So this course will be, this assignment will be mainly on fault analysis, the different kinds of faults that we see in power system networks. We'll try to solve all of the problems because more or less these are easy provided you know the formulas and stuff. So let's start. Question number 1. The series impedance matrix of a short three-phase transmission line in phase coordinates is this. Now, the series impedance matrix, which is the standard matrix formula, if you see, is this, right? Where your ZS is the series impedance of that phase, then your Zm is the your, what should I say, the mutual impedance of particular phase with the other phase, and your Zn is the neutral or ground impedance. So if you compare these two matrices, this one and this one, you'll notice that there is no ground impedance there. So that is why Zn is 0. Now, when you take the inverse of this, do that analysis when you try to find out the, the zero, then the negative and the positive sequence impedances, you get this matrix where your this is the Z0. So Z0, the zero sequence impedance, which is called, so this is ZS plus 2Zm, and your positive and negative sequence impedance is ZS minus Zm. So here they told that if the negative sequence impedance is 1 plus J10, so your Z2 is 1 plus J10 ohm and Z0 is 4 plus J31. They have told us to find out what is the imaginary part of Zm. So this is very easy provided you know this formula. So your Z2 is this one and your Z0 is this one, and you know the relation ZS and Zm. So this is ZS plus 2Zm and this is Z2 is ZS minus Zm. So what I did, I basically did Z0 minus Z2. So from here I am getting 3Zm equals to 3 plus J21 and my Zm is 1 plus J7. So my imaginary part is 7, which is my option number B. It was pretty simple problem. So I hope, this should be clear. Now let us go to the second problem. I just keep checking on whether the recording is going on. So, yeah. Anyway, so in question number 2, at a 220 kV substation of a power system, it is given that the three-phase fault level is 1000 MVA and the SLG, so single line to ground fault level, is 1250 MVA. Now, neglecting the resistance and the shunt susceptances of the system, find the zero sequence driving point impedance in ohm. And of course they have told that assume that the positive and negative sequence driving point reactances are identical. So we have been given this two information that the three phase fault level is your 1000 MVA and SLG fault level is 1250 MVA. Now for this analysis I have considered this to be the base. So base voltage was this, and I have considered the base MVA to be your 1000 MVA. You can consider 1250 also and then proceed, or maybe any number, maybe it could be 100, 500. You would, at the end you will get the answer, correct answer, if your steps are okay. So MVA means basically current into voltage, right? So in terms of base, so we had a fault MVA of 1000, right? So I have divided 1000 by 1000 here to to do the analysis in per unit, and we have the fault point voltage to be 1 per unit, and your fault voltage IF, fault current is IF, which we have to find out, three phase fault current. So it comes out to be 1 per unit. Now when I do the same analysis for SLG fault level, so I get the fault current of single line to ground fault to be 1.25 per unit. Now they have told that yeah, so basically okay, so in the question, neglecting the resistance and the shunt susceptance, find out the zero sequence driving point impedance. uh, So here what I did, yeah, okay, so it is pretty simple. We know the formulas, right? So your SLG fault ka formula we know. So it is three times the positive sequence current. So in single line to ground fault, you have the all the sequence currents to be equal, right? I1 equals to I2 equals to I0. So here I have just replaced that formula, and this is the your ground to neutral, I mean neutral reactance that we connect. So here, since we have no information on that, I have kept this to be 0. So 3 into 0, and your Z1 is the positive sequence reactance, Z2 is the negative, and Z0 is the zero sequence reactance. Um, so here we have been, so here basically we found out, right? Okay, so before that we have this formula. So for three phase fault, it is pretty simple, right? It is the fault point voltage divided by the positive sequence reactance, right? So Z1 is coming out to be 1 per unit for your this three phase fault level, and here they have told that the positive and negative sequence reactance are identical. So Z1 and Z2 both are 1 per unit. So here we just replace this. So Z0 comes out to be zero point 0.4 per unit. And here they have told to find out the value in ohm, right? So I found out the base reactance from this, base impedance basically, and multiplied this with the per unit value of Z0. So this came out to be 19.36 ohm, which is your option number B. So I hope this was clear. I mean, this calculation stuffs that we did here.
Yeah, yes.
Okay. Yeah. Now let us go to question number 3. So here they have told for a fault at the terminals of a synchronous generator. Mind this word. So at the terminals of a synchronous generator. So the fault MV is maximum fault. So they have given these 4 faults. Now to solve this, you have to keep two things in mind. First of all, where the fault is occurring. That is very important, because so here they have told that it is occurring at the very beginning, right, at the terminals of the synchronous generator. And here I have shown the formula, written the formula for every kind of fault. So this is line to ground, this is three phase, this is three phase to ground, and this is also line to line fault. So basically what we know, that as the length of the transmission line increases, your zero sequence reactance also keeps on increasing, right? Because at the terminals of the synchronous generator, your Z0 is very low. So and also if you see, your line to ground fault is three times that of the your positive or negative sequence current, whatever you say. So that is why, I mean, this line to ground fault is considered to be the most severe at the terminals of the synchronous generator. Now, if you say that if I consider the fault to have happened at the very end, so some far away at the transmission line, then you can say that your line to ground fault won't be that much severe, because you have a considerable amount of reactances which is adding up. So in that case, yours, because you have a high Z0 value for a long length of power system, so considering transmission line, transformers, and your synchronous generators. So in that case, your three phase fault would be the most severe. So because they have told us that what would be the, I mean, level, how much would be the current severity of the fault at the terminals of the synchronous generator. So that is why for this your line to ground fault would be the most severe. I hope this was clear. My explanation, I hope this was clear.
But three-phase would be having higher MVA value, right? Higher short circuit MVA compared to.
No. First of all, see, you have two considerations. First of all, see, this three term is there, which you won't get here or here. This is because your fault current is three times the sequence current, right? I1, I2, and I3. They are both equal. And secondly, your Z0 is very small for synchronous generators. And your Z1, Z2, they are also, I mean, not that large, right? So that is why, I mean, this would be much higher than this thing. So I also had a confusion with this. This is the reason that is, I mean, mainly given by the authors in various
Okay,
kind
and
of
what
books.
happens? Let's consider this case alone,
Hmm.
three-phase fault and
Hmm.
LG fault. Okay,
Hmm.
what happens if fault is happening at far distance? Because I'm also going to have the same
Yeah,
value, right? 3VT is
yeah,
still
yeah,
going
yeah.
to be there.
Yes. So then see, if it is occurring at a far away point, so you have a sufficient amount of zero sequence reactances that are getting added up, right? Because you have your synchronous generator, then you have a transformer, then you have a transmission line, right? Then your denominator gets I mean, it gains a certain amount of value. So in that case, the level of the fault would get reduced, and as a result, in that case, we will say that our three-phase fault is more severe than line-to-ground fault. Did you understand this? So basically, I mean, as the length of the line keeps on increasing, the importance of Z0 also gains more importance.
Okay. So that will
Yeah.
be compensating the effect of three
Yes.
times the
Yes.
voltage, so
Yes.
the
Yes.
current will
Yes.
reduce. Okay.
Yes. Yes. Yeah. Okay, so I'll come to question 4 later. Now let us go to question number 12 directly. So for solving question number 5, we need to know, how we draw the zero sequence reactance diagram of a transformer. Because you see in this figure number 5, we have star delta transformers, then star star transformer with a resistance grounding. So just okay, yeah. So here basically what they told that this is a two bus system, and the corresponding the your is I mean, this is a system power system in 12.1, and its zero sequence reactance diagram is shown in 12.2. So here you see that there are two transformers, right? T1 and T2. So they have told us that looking at the zero sequence reactance diagram, what would be the type of the transformers T1 and T2? So is it a delta star, or star star, or star delta? So I mean, for finding out, this is very easy. So we have to just keep these. So I have drawn here. I hope you can clearly see that. So let me just zoom into this so that you can see it more clearly. Yeah. So here I have considered three configurations. Okay. So this is a transformer in a power system network where the left hand side is star connected, where there is no neutral grounding, basically grounding, and on the other side we have a star connection with solid grounding. So the connection, I mean, the zero sequence diagram would be something like this. So your left hand side would be open because there is no grounding. I mean, whether it is solid grounding or resistance or reactance grounding. So that is why this would be open. And the other side, since this is a solid grounding, you would basically short these 2 points. So this is a configuration that is followed. Now the same here, I have just replaced this thing with a delta. So basically this would remain the same. On the delta side, you would have something like this. So this would get opened, and you would have something like this. So basically this would be a connected directly to the ground, and this end would remain completely open. And if it is a again, this side I have kept constant, and here I have done a star with reactance grounding. So basically what we were doing here for the first diagram, we were directly shorting these 2 points, right? So we will be basically representing this with the this reactance value. So this would be 3 times xn, right? So this is the convention which is followed, because this is directly connected to ground. So basically 3xn. So this is these things you have to remember, and then you have to draw the zero sequence diagram. So
Um,
if we
uh,
yeah
I have a question here.
yeah, yeah.
Actually, this one I have noted in the session also, but I could not ask
Okay.
it. You take the first connection, star ground.
Ha ha.
Okay,
Yeah.
here in star ground, we are representing the impedance on the right hand side, right? But how it
Hmm.
is going to make a difference if I'm representing that impedance on the left hand side? Both, again, I'm not going to have a zero sequence current flow between the transformer or in the circuit, right? Why should I mention only on the right side? If I, what will happen if I mention that xt on the left side? And similarly, you take for a star delta also. There also, I'm not going to have a zero flow. So what would happen if the impedance is mentioned on the left side? Why I am mentioning in
Okay,
that
okay, I got
way?
it. Yeah. So suppose you have a synchronous generator on the left hand side, and what would happen to the reactance, zero sequence reactance of that, right? That is what you are asking, I guess.
No, we just consider this the first one, star grounded.
Hmm.
In that,
Hmm.
the xt is mentioned, right? Let us
Hmm.
consider um, it is okay per unit system, but still we have mentioned it in the star grounded side, that impedance is mentioned in the star grounded side. What I'm asking is, if you mention the impedance, the zero sequence impedance in the star side,
No, no, no. Lakshman,
how it
this
is
is
going
not
to
the.
be
No,
different?
this, see, this XT is the. I mean, this is you are doing the analysis in per unit, right? So this is the. I mean, you can't consider it to be on the left hand side or on the right hand side, because while drawing the zero sequence diagram, it is just the this impedance, the this middle may the thing which I have drawn. This xt is the impedance of this thing, the winding, right? This is not the impedance on the left hand side of the y or this.
No, no, no.
Uh,
That I understood. Even
yeah.
if I'm going to represent in any side, the impedance is going
Huh.
to be the same thing. Okay, that's fine.
Yes. Yeah.
But
Yeah.
uh, what I'm asking is, instead of this, how to can I
I
request
mean, are you
access?
asking that what would be the consequence? I mean, net consequence on the fault level or
No,
something
no,
like that?
no, no, no. If what will happen if I'm representing this xt on the left
Okay.
side and keeping this that two dots on the right side open?
Okay. You can't represent that, right? Because this
Like
is a
now,
power.
I'll tell another way. Right side, the two dots are there, right? You have connected that one. You
Yeah,
open that
this
one,
thing. Yeah.
and left side that is two or open, right? Just make short. How that will
See,
make the
yeah.
difference? Both are same, right? Or I should not
No, no,
represent
no.
in that way?
See, mm,
Why I am representing in this way instead of that way? Because what I'm understanding, both is going to be same thing. I'm not going to have the zero sequence flow. Anyway, the circuit is open. I'm not going to have the flow at all. So what is
see,
the difference?
basically, suppose you have this thing open. So if this thing was reversed, right? So this would have been short, this would have been open. So as a result, the your the net impedance on the left hand side would have a certain value, and on the right hand side it would be infinity, right? Because the circuit is open. I mean, if you would have had an extended power system network on the right hand side, suppose you have a transmission line, then another transformer, then a load, synchronous motor, you have every zero sequence reactance which is present there, and you are trying to find out the net impedance. So if this was open, then your the Thevenin reactance which you call, so we have a sum on this, we do have a problem, so that would have been infinity, because this would have been open. And and I mean on this side it would have been your this reactance plus the reactance of the synchronous generator. I mean this is what I hope, I mean what you are asking.
Yeah, you understood my question, but I still don't find the difference between these two methods of representation.
No,
And
no,
anyway, I'm
this
going to
will
have,
have a, this will have a significance. So, I mean, see, normally you don't, in power system network, you don't see this kind of a thing. You mainly see this either solid grounded or this kind of system and another delta. So what this does, since you have this ground impedance, it increases your net impedance of the system and it reduces your fault current level. And you have to have a delta on one side of the transformer because your circuit gets open and you have a very high, I mean infinite impedance, what they call. So Z0 is infinite, so I mean your fault level gets reduced. So basically in power system you have a star with grounding and delta on the other side.
okay.
I hope, I mean I was not able to clear your doubt, but to some extent, I mean, you might have understood what I am trying to say.
Yeah, I got your point, but still, still I don't get it. Anyway, I will read some other books, or I'll refer some books also on this thing. I'll put it another way. How you are represented XT in this method? We have plotted, right? You have taken one point as a reference and you plotted the XT. So how you have plotted this diagram from star star ground? How do we arrive at this circuit?
See, this is a single line diagram, right? You are making it complex. So you are thinking of a three-phase circuit.
No, no, no. I'm very clear. It is a zero sequence impedance. I'm very clear. I'm going to
Huh.
take only one impedance.
Yeah.
Um, if I'm changing the left side thing, the
Huh.
SLD into the zero sequence diagram.
Huh.
So initially, see, this is available in the session as well as the recorded session as well as books. Also, I could find the same thing.
Yeah.
But why they haven't taken the left side as short and right side as open? Why they have taken in this method?
No, no,
So
no.
for me,
This is the, this is not a fixed convention. It could be left hand side could be shorted, right hand side could be open. This is a convention, right? If this would have been shorted, we
I'm not
would have
saying the star
taken.
connection. I'm saying about,
Okay.
let's have the same diagram.
Uh,
The first set of dots are there, right? That we have kept open. The second set of dots are
yes.
there that we get short, that has been shorted. Okay, we are
Yes.
having written path to ground. My question is,
Yes.
if first set is shorted and second set is open, that is that is not at all going to change anything. That is what I am understanding. Okay,
No,
anyway, I
that is
will.
going to affect your system a lot because see, you would have, so see, if this would have been open, right? And this would have been closed, so you would have, that is what I was trying to tell you. So you would have a large system connected to the right hand side of the transformer, provided you have a synchronous generator on the left hand side of this. So you would have added impedances of that system also, so that would really affect your system. So this
Yes, in that
convention.
case also, I'm not going to have
Yes.
a. Let's consider I am having a very big system on the right hand side, but still I'll not have
Yes.
a zero sequence current flow into the system at all, totally, because if
Yes.
I'm
Yes.
shorting left side
Yeah.
or
Yeah.
right
Yeah.
side, the current is going to be always zero sequence because I'm not having the continuity of zero sequence current, so it is
Yes.
going to
Yes.
be
Yes.
zero only.
Yes,
So
yes,
I,
your impedance would be infinite. Yeah, that I agree. Okay, so you are trying to say how does it affect,
yes,
right? Hmm.
okay then. Yeah, we can
Yeah.
continue this. Yeah, I have taken too much time. Sorry, you can
No,
continue.
no, no problem. No problem. So, okay. So, anyway, so let us go get back. So, here you see that XGT1 both sides are shorted, right? So, you'll understand. I mean, clearly you understand that on the left and right side it is star with a grounding, right? So, you immediately see that option C has this thing. And if you see on xg2, So xg2 mein left hand side is open and right hand side is shorted. So you have delta on this side and star on this side, grounded star. So which is your option number C? I mean delta grounded and star. So I mean, see, if in this system you have a, you know, somewhere fault is occurring, let's say as at bus 2. So you would be, you know, your what should I say, star delta or delta star with a grounding would have significant consequence, right? Because if this would have been connected, so both would have been star, 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 everything is star, you would have a certain magnitude of impedance, right? Because this would have been a closed circuit with a fault at one end, so you would have got some impedance, right? But now since this side is open, so this would make only this closed circuit, right? So we would have a very small impedance, right? So this would be what, let's say this is 1 per unit, this is also 1, and this is 3 per unit, so 5. So the net impedance is very low, right? Zero sequence impedance, and as a result, if we have a fault at this point, the severity of the fault current would be really very high. So that is why this kind of, you know, what kind of configuration of transformer that you use severely affects your system. I was trying to highlight that point only to you when you are trying to ask this question. That how does it
Okay.
affect? How does star or star delta? I mean, in a whole, in a nutshell, it affects the, you know, severity of the fault. How large your fault current would be. I mean, you try to protect your system, that you try to add more and more impedances to your system to reduce the fault current level. And I mean, you try to choose your system in such a way, the transformers in such a way that I have a delta on one side, right? Because then somehow my, if my zero sequence impedance is infinite, it would serve my purpose. So we do have a problem on that. I'll
Here
take,
in this question itself, a
yeah,
transformer 2 you take, if it is
yes,
star grounded,
huh, yes,
still I'll be having the same circuit, right? How it will differ?
no,
If
yeah,
star grounded
then,
is there,
huh.
my zero sequence current I'm going to plot in the same way. If it's star grounded, I'm going to take uh,
No, both side, if T2 is both, I mean, this kind of configuration, then we would have a zero sequence reactance, right? If T2 would have been only star and this is star grounded, then we would have something like this open circuit, right? Your Z infinity would be, I mean, Z zero would be infinite, right? Because open circuit.
okay.
I hope, yeah, I hope you understood this. So basically this thing, right? So that is why I was trying to tell you that these do have significant consequence, this kind of configuration.
Still that open circuit is available. You can see
Yeah,
x01
this
and
is open
x0, that
circuit.
open circuit is available.
Yes, this is, but you have this loop right here. And if you have a
Yes.
fault at this point, you do have a certain impedance, right? Let's say your fault is occurring at the motor terminal. So you do have some, or let's say at bus number 2 at this point, right? So this would be something like this. I mean, this point would be shorted. So you would have a certain zero sequence impedance, right? You will
Okay.
be having.
Okay.
Yeah. So what I was trying to tell you is in question number 5. Yeah. So see, here we have this circuit. You see, this is star grounded delta and star with a resistance. So yeah, this is resistance. Sorry that I drew like this. So this would be resistance and not impedance. So here they have told this is generated feeds another transformer through a short feeder. The zero sequence values are expressed in per unit. Find out the Thevenin equivalent zero sequence impedance at point P. So this is the point P. So see, we just now saw this, right? So this is your 0.35. So this would be resistance, not impedance. Sorry. And then we have this zero sequence impedance. So see, that I was saying, you know, I mean, you can see they have given this x0. So We were discussing question number 3, the fault level at the terminals of synchronous generator. So I was telling you now that x0 for generator is very small. So as you go on increasing, further away from the synchronous generator in the transmission line, your reactances, zero sequence reactances keep on increasing. So you can see it's very low here, 0.05. So that is why your single line to ground fault level would be really very high as compared to uh, a three-phase fault. Anyway, so this is 0.05 and we have this thing. So this point would be shorted. Then we have this x0 and then this is delta, right? So this is delta. And now again this is the transmission line 0.09. Again this is star with no grounding, right? This will also be open, and then we have this 0.12, then this is 0.35, this would be resistance, and we have this
Hello? You're not audible.